All right, hello everyone. This is going to be just a quick introduction to section 10.1, chi-squared test statistic. We did this in class, or at least the first year I did. So we did this in class, so many of you will probably not be watching this, but just in case, I'm going through a little quicker. So the idea is this: the chi-squared test statistic is a test statistic that allows us to put a number on how far apart two lists are. So what you have here is you have an observed data set. So this is just rolling dice. So I just rolled dice 60 times. Okay. And I got 12 ones, 9 twos, 10 threes, 6 fours, 11 fives, and 12 sixes. All right. Is that what I would expect? So clearly, because we know a little bit about probability, I would expect 10 of everything. So now the question is, how far apart are my two lists, basically? I have hypothesized, so my null hypothesis would be something like 10 each, right? That's my null hypothesis, 10 each, and not 10 each, something like that. We'll talk more about our hypothesis later on. This is just a quick introduction. So now we're going to gauge how far apart these two. If you look at those two numbers, you probably say, maybe they're not too far apart, probably okay, but maybe you would say no, that there are too far apart, so there's something wrong with the die, maybe. So we kind of just talked in class about what's a good test statistic. We talked about we could just subtract, observed minus expected, and add them up. The problem with that is some are over and some are under. It's going to wind up being 0, actually. So that's not a very good way to do it. So mathematicians then thought, hey, let's just square it, because then we get rid of that negative piece of it. So that's better. But the problem is, I have a little example here, and I'm going to save some time. If you notice, these two problems, same thing. The first one for die A, I rolled 60 times, but the second time I rolled 6,000 times. And you might notice difference of 5, 6, 8, 6, 5, and 2. And here a difference of 5, 6, 8, 6, 5, and 2. The differences are exactly the same. Okay. But I think you would say that there's probably an issue with the first die. Like, look, they're really far apart from 10, but there's not an issue with the second die. They're almost right on. So clearly that observed minus expected squared is not a good test statistic for that. So what turns out to be the test statistic we want is just simply this. This is called a chi-squared test statistic. You take the observed minus expected and you square them. And then you divide it by the expected. So that brings into play the sample size, because the bigger the sample size, you would expect a different answer, basically, right? So, and then we divide it by the expected value. So that's our chi-squared test statistic. So I'm just going to go real quickly just to run you through doing one on your calculator. I know I'm just going to have to walk you through it again. Sorry. But what I have is these are list 1 in my calculator. The observed, my expected are list 2. And then I have a third list, which is just observed minus expected squared over expected. So I'm going to type it in for you. So right now you're going to have to listen to me, I know. But I'm here in list 3 right now. So I got the numbers 12, 9, 10, 6, 11, and 12 in list 1, and the 6 10s in list 2. And then I'm going to scroll over list 3, put my cursor up at the top. And I'm going to go list 1 minus list 2 squared. That's my observed minus expected squared. And then I'm going to divide it by the expected list 2. You could do this by hand. There's only 6. It's not that hard. You could do, it's just, look at the numbers, right? It's 2, it's 1, it's 1, it's 4, it's 1, it's 2. Square them, right? So 4 and 1 and 1 and 16 and 1 and 4. And then divide each one by 10. They're not always going to be 10 each. The next problem, the expecteds might be different. But then I just divide by 10, 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 and then add them all up. And I get a test statistic of 2.6. The question is going to be, how big is 2.6? Is it too big? Is it not too big? And that's what's coming next. This is just a really quick introduction to how to find its chi-squared test statistic. So you would have some preconceived idea. It's like our guess, right? It's like our hypothesis. In this case, our hypothesis is 10, 10, 10, 10, 10. The next time our hypothesis might be for a different problem. It might be something completely different. They don't have to all be 10s. Then you take a sample, and then you compare your sample to your your guess. And then we're going to figure out, again, where are our cutoffs, how big is too big, how do we run a test, and all that other stuff. This is just a quick introduction to finding that chi-squared test statistic.